we still call them refugees, and sometimes they are facing a lot of challenges. Sometimes it's related to their ethnicities, on the religion or their background or the race. And these people, they're just like us. They had a normal life and they would never be in our land, if their country is not in war. And many times, because of the discrimination that they face, they don't have equal opportunities. They limit access to a lot of essential things in their daily life: food, shelters, education for their children. And we want to understand the reason for that and why some refugees are welcome and why some refugees are not. And if this is really the case for normal people like us. So I want you to see a video. It's not a long video, and then we can continue the discussion. Oops, hold on a second. I think I need to stop them. So. Yeah. This one.
Isn't a place, with all due respect, like Iraq or Afghanistan, that has seen conflict raging for decades. This is a relatively civilized, relatively European. I spoke in a way that I regret, and for that, I'm sorry.
So I see European people with blue eyes and blonde hair being killed, children being killed every day with Putin's missiles.
On parle pas là de Syriens qui fuient des bombardements du régime syrien soutenu par Vladimir Poutine. On parle d'Européens qui partent à leur voiture, qui ressemblent à nos voitures, qui prennent la route et qui essayent juste de sauver leur vie, quoi.
So let's go back to the presentation. So I think you got the idea here that some refugees, if they're brown, if they're not white, then maybe we shouldn't welcome them as much as white people. Now, why this is a computer vision or an HCI study, and it's not in the social justice department, we wanted to see if we can test really the bias in users, in normal people like us, in a controlled lab away from the media. And if we can measure this bias and see if it really reflected the journalists and the media, okay? And in order to do that, we wanted to apply computer vision technique to see and to change a little bit of these refugees' shape and, the way they look. Okay. So now we see that there is a bias towards Syrian, and Ukrainian refugees. The stereotype that, they're uncivilized. And the thing that a lot of people don't know, that there are Russian military operation in Syria and Ukraine, but a lot of people, they don't know that. So this is a very good study because we are using people who are affected by same entity. Okay. So there were very challenges with the asylum system, and the government keep failing those refugees. And there is usually an anti-refugee sentiment among people, and that's what the media is showing us. And the Syrian people, they face a lot of discrimination during this process of fleeing their country to go and try to find a safe place. Now, the study of bias is not something new in this study, but there is a lot of human-computer interaction and machine learning to detect the bias in the user. And usually when they detect the bias on gender, on race, on ethnicities. Our study is the first one to use it on refugees. So usually that we investigate this potential bias and we use eye tracking. So that was our goal. We're going to use an eye tracker after we use a computer vision techniques on the data set of the refugee images. And then we're going to analyze how the user, like participants, they interact with these images. And we will see what we can get from their eye movements, from the pupil dilation, and all this that I'm going to explain later. And I just want to say that there is a research gap in general in refugees informatics. So this is one of the things that we are still behind in terms of computer science research. So there are like previous, articles that, highlight this discrimination and how you can detect those with research studies. Okay, but what we care here about is how can we link it to eye tracking and social psychology. Okay, so the eye tracking is a very well-established method in social psychology, and it can read the people's cognition without interfering in the task, because you can detect from their eye movements, from their pupil of the size, how much they are engaged in your study without asking them, without any need to make them write a survey. And the system has been for around maybe 50 years ago or maybe 60. So the analysis is already established, and we understand what this eye movement is doing when we see it, in the data. And there have been many studies in HCI that use the eye tracking for bias detection. And usually when we are talking about using eye tracking, we're talking about the cognition, okay, and measuring and detect the cognition. And we can like imply that, okay, this measurement of the eye tracking that measure the cognition can relate into the bias. Okay, there was a study, I think it was published 2 years ago, that it measured the gender bias, and then it in the middle block of the users participating in the study, it started to see if we can untrain their bias. So what they did in that last study, that they show them images from different genders, so the two genders, and they asked them to choose the gender into a specific, art background. And this art, sometimes they are doing intellectual activity, like they are reading a book or playing an instrumental music. And sometimes these art images, the person and they are doing nothing. So they're just posing. And they found that in the first 10 trials, that people tend to choose women with the images that they are just posing and doing nothing, while males to the images that they are doing intellectual activity. So what they did is, in the middle block, they give 2 images, both are females, and also all the art images were for people who are doing intellectual things. So they start to force them kind of into choosing a female with an intellectual activity. And then the user get the idea that, yes, I can match a female with, a picture of reading a book. After that, they test them again into another set of blocks, and they give them men and women again with the images of art. Some of them they're doing intellectual activities, and some of them they don't do it intellectual. And they found that in the block after the training block, the participants, they tend to use more female and match them with art that they do intellectual things. So this is kind of like a way to detect the bias on gender and then to untrain their bias. And they use also, then they use an eye tracking for that. And they measure how their pupil size when they see an image of a female versus a male. This study was for, they first did it with Mechanical Turk. So they had like around 360 participants. And then they replicate the study on the controlled lab in an eye tracker. And they had like around 20 participants. So there are, there is, a promising thing when we are using eye tracking technology to detect the bias of the user. Okay. Some other studies, they also do machine learning to also detect the bias. Okay. So there are previous studies that they use eye tracker and they collect the data and then they use machine learning on those images or on the data that they have to classify it, whether it's a bias or not. So here's also another possibility when we see that, machine learning start to engage in detecting and classifying the bias on the data that we get. Okay. So here, one of the challenges that we have is we don't have a data set first when we wanted to do the study. So we had to go and collect the data ourselves. When we had to collect the data, we were careful to use images that are truthful. So we don't use images generated by AI or fake images. So we had an artist who helped us to go and look for those images. Most of those, we found that they are for women or children. And that's because another study that they call Reading the Mind and the Eyes, this study, they found that people, they don't have the same sympathy when they see men, refugees, versus when they see women or children. And that's why if you go home now and if you try to Google images of refugees, probably most of the picture you will see images of women or children. And even if you ask an AI to generate an image of refugees, probably it will generate an image of a woman or a child. So we found very, very few images of men. And with that, we thought that, okay, we can't use it because we don't have enough images of men to make a conclusion. So we excluded all these men refugees and we used the women's refugee because there are more. And we were able to find them. That study, Reading the Mind and the Eyes, also found that there is bias when it comes to the refugees with age. So there are also more, people have more empathy when they see older people than they see young people. So all these put challenges into how to collect those images. The other ones that we also want an images of people who are posing to the photographer. So we need, images of photographers who went to those onto those refugee camps or places, and they took a picture while the person is posing to the camera, because we want the face to be clear later when we start to apply the computer vision techniques. Another thing that we found that was challenging is the quality of the images. And by the quality is not that how clear it is. We already decided we want a very high quality. But we also found that the Syrian refugees, they are more, that they look more, what we say that they are not polished like the Ukrainian refugees. So you see the Ukrainian refugees with clean clothes, a clean face, and posing to the camera. While for the Syrian, they like their face, like they have like this dust, in the clothes they had dust. And the reason for that is because the journey that those Syrian refugees took to arrive the land was more tough than the Ukrainian. For the Ukrainian, they only need to open the border on the other European country and they pass. Well, for Syrian, usually they have to go through a boat, and then some of them they have to walk in a desert. So by the time they arrive, they look different. So that was one of the challenges, because we don't want, when we put these images, we don't want other factors to affect on the people's choice. We want them to be equal. So we started to look more into these Syrian refugees to find some of people who are a little bit polish and clean, so we can compare them with the Ukrainian refugees and when we put them to the user, that this factor, that they are more, tired and they have a tougher journey, won't affect, in the people's choice. Because our goal, we want to see if the ethnicities or the background is the factor. Okay. So we were able to collect from all these refugees images on the internet. The only one that fits with the category that we want were 40 images. I know this is very, small number, but this is how we do things. When you are in a controlled lab, you really need a very high quality data. So we have a 40 image data set. And they're all high resolution, and they are taken by professional photographers. And we had the same number of the Syrian and the Ukrainian refugees. All of them are women, okay? So now here we started the computer vision. What we did here is we swapped their faces, okay? As you see in the video, and this is why I wanted you to see the video, that they say those refugees, they have blue eyes, the blonde hair, they are like us. So that was the idea. Let's swap the faces, let's swap these blue eyes and blonde hair, and let's see if people change their empathy, okay? So in order to do that, of course, we can do it with Photoshop. It will be obviously clear that it's fake and it's Photoshop. So we had to use AI for it. So we utilized many techniques here in order to make this swapping, natural, and the participant won't feel it. So we use different things. One of it is the Python-based script with an OpenCV library. Now, every one technique of those would do a different things into the face image. So we use a facial landmark points to identify the area where we want to make the swap. We also use an ordinary preprocessing analysis, or OPA, and that's mainly to create the mask for the eyes and for the nose, for the eyebrow, and for the nose and mouth. And then we use singular value decomposition, and that's to measure the points and to do the rotation of the face so it can match a new image. Okay. So the OPA is the one that helps you to find those landmark points in the face. And this is an example of what we did. So here, the OPA will turn the faces, the one that you want to take and put onto the other face, those two faces, it turned them into objects. So now we are dealing with two objects, and you need to compute the similarities between those two objects. Okay, so here we take the difference in the two objects. We do this, first of all, we translate it to match the image. So we have two images. We take the face of one image and we drag it into the other refugee images. So that's the translation thing. And then we rotate it using the singular value decomposition. And then we scale it. Okay, sure. Yeah, no worries. Okay. So yeah, so we created the whole experiment using a MATLAB. And that MATLAB code was able to run the experiment, detect the user's responses, and also give signals to the eye tracker to record the eye movement data on the screen. Okay. We used 18 displays. And now you're going to ask yourself, okay, you have 40 images, and now you downsize to only 18 trials or 18 displays. And the reason for that is some of these images, we use them to swap faces, right? So that's why, you know, every trial you can think about it that maybe it has 2 refugees images, okay? So some of them, when we are trying to swap the faces, we think we didn't get a good numbers, that the face didn't really had like the difference between the landmark points were not good to create this swapping. But most likely because we are using 2 images at a time, so that's how we downsize the number of the trials into 18 trials. We divided those trials into 3 blocks. And these blocks will give the participant a chance if they want to take a break, and also to alternate between the conditions that we have. So what are the conditions? This is how we give an image of a person. Is it also still unmuted? Sorry? Oh my goodness. Oh, sorry. Yeah. You can see it now? Yes. Okay, good. So this is the first, so we had 3 blocks. The first block is you see the original image of the refugees. And we give you a label of what is this image that you are seeing. So you're seeing a Ukrainian refugee, and that is true. This is a Ukrainian refugee. And then we ask them, how much would you like to donate? So they can hit, you know, Z or C based on 1 or 10. And the reason for that, why we give them, you know, 2 options that are just keyboard. We want to keep their hands on the keyboard onto very simple tasks that they don't need to look down to type, because we are recording their eyes. So if they want to donate $1, they can press Z, $10, they can press C. In the block 2, they see a swapped face, but they don't know that this face is swapped. So this is, the background is still the same. And we are saying that this is a Ukrainian, but actually here, we are using the computer vision to change it to a Syrian refugee. So they don't know that they are seeing a Syrian because they're seeing the Ukrainian, right? We do the same thing with the Syrian. So we also give them an image of a Syrian, or original image, or an image of a Syrian with the face of a Ukrainian, okay? With a label that always stays with the original image of the background, okay? Then what about the third block? The third block is called multi-donation block. When first they see the real image and we ask them to donate, but we tell them that this trial is actually divided into 2 trials. So that's why you see we have only 18 images, because some trials has 2 refugees also. So here in the first one, we show them the real image. In the second one, we show them the same image, but with the face change. So here, the participant knows that this is not the real one, because they just saw the first one and then they saw the same image again with the face swap. So here, the participant, they know that there is some swapping. So they didn't feel it in block 2, but they see it in block 3, okay? So every block consists of 6 trials. 2 trials for block 2, for block 1, 2 for block 2, and 2 for block 3. So, and the idea of doing 2, 2, 2 is because we want to remove any learning effect. If you see all the first trials, block 1, and then we give you block 2, now the participant is expert, they learn. And now here you don't know, am I measuring, the effect of block 2, or am I also measuring that they have become good at the experiment? So this is when you divide the task into blocks, and then you alternate between conditions, you kind of cancel the learning effect of having the same block at once and then the second, or the same condition first and then the second condition. So this is why we have 2, 2, 2 for every block. So condition 1, condition 2, condition 3. Okay. And also we have a 16 seconds for every trial. So we put the image and we give them 15 seconds. If they don't answer, we just move to the next trial and we just consider that there's no response. We have to give this option, because you can't let them look at the picture forever, right? You want to time them. So 15 seconds for every trial. Now here we took, some measurement. What do we want to measure? We want to measure, if the RT, the reaction time. So if the reaction time is 1,000 milliseconds, okay, which means 1 second, they answer a donation in 1 second, then maybe they're just pressing without thinking. So those trials, we just delete them from our experiments. Okay. So that's one of the idea that we got. Okay. So participants were alone in the room. We didn't interfere with them when they did the study. Study in eye tracking, it has to be very controlled. So we need to minimize also the noise from outside, because everything can affect on how people, think, and then affect on the measurement of the eye movement data. So they were like in a closed room, in a closed lab at the campus. We give them a task, practice test. And with that practice test, we show them the 3 kind of conditions, but then we don't include it in the analysis. And it's not one of the ones that they've seen in the actual experiment. That to make them, familiar with the study. So if the actual experiment starts, you don't want them to ask you. You want them to be familiar and they know what they do, because we sit very far from them. So here are the 3 metrics that we use to measure this experiment. Is the reaction time, how fast they can, decide on the donation that they want to make when they see Ukrainian versus Syrian, when they see the original image versus the swapped, or when they see the image in the 3rd condition, when we flip it and we make them see it. So the amount of the donation, also something that we wanted to consider, and the pupil size. So the pupil size reflects people's anxiety, happiness, sadness. So it reflects our emotion. It also reflects our cognition and how we are doing tasks like math task, memorization, searching. Those all affect on our pupil size. And also there are other factors that we all see, is the light. The light can also affect on your pupil size, right? So all these were controlled because we want to compute the average of the pupil size during the entire trial. We also have, if you remember in the trial, in the display, we had a background that is gray. That's also to limit the brightness that can go into the eyes. And then we had the eye movement data, and we had also the user response. So we had to analyze them, and we used for that Python script that we just wrote it in the Google Colab. Okay. We did a 12T test, and those 12T tests, because we want to measure the difference between the donation, the reaction time, and the average of the pupil size, and condition 1, condition 2, and the 3rd condition for both Syrian and Ukrainian. So with all that, we create 12. Okay. We also did a 6 analysis of variance to analyze the difference in the means for the pupil dilation, the donation, and the reaction time. in these different blocks. Okay, so the result is a little bit interesting. And I also, I call it, you know, some promising, and it gives me hope into humanity. So we found that there is no, when we look at the block one is the original image of the Syrian or the original image of the Ukrainian with the label of Syrian or a label of Ukrainian. So there is no tricks here in block one. And we found that there is no significant difference in the reaction time or in the pupil dilation or in the donation when we present a data of a Ukrainian refugee or a Syrian refugee. The participants, they donate the same. And their reaction time to make the donation was the same. And even the pupil dilation was also the same. Okay. In the block two, when we swap the image, so the body of a Syrian with the face of a Ukrainian and an image that says Syrian, or the opposite, where the body of a Ukrainian with a Syrian face and a Ukrainian label, it didn't make any difference in people's donation. It didn't make difference with people's reaction time. And it didn't even make a difference in people's pupil size. In the block three, if you remember, we showed them two images. One image is with the real data, and the other image with the same image, but we swap the face and we make them see that we are swapping the face. Okay. So the first image, when they see an original face, they didn't make any difference whether it's Syrian or Ukrainian when they see in terms of donation, pupil dilation, or reaction time. Now, in the other one also, when they saw that the image changed, they don't make a difference. Then where is the difference that they make? So here, with the two-way ANOVA, we notice that the Ukrainian refugee trails also is not significant. So here, so B1, B2, B3I, and B3F, it means that the condition 1, condition 2, condition 3, the first image, and condition 3, the final image. So the initial image and the final image. And we found that there is no difference between all the three blocks within one ethnicity. And also the second one, with the Syrian, also there is no difference. So now we are looking within one ethnicity. And we are finding that the block also, whatever you show them, it doesn't change how they perceive the data. What we found is that with the two-way ANOVA, whether you show them a Ukrainian refugee or a Syrian refugee, that there is a difference between the initial image and the final one, the one that we swap it. So if you are showing them an original image of a Ukrainian and then you swap it in block 3, then that creates a difference in the donation that they make, and it creates a difference in the pupil dilation and the reaction time of the making donation. And same for Syrian. So here, the user reacted to the originality of the data, if the data is authentic or not. If it's not authentic, and they feel that it was manipulated images, then they lack their empathy immediately. And we didn't feel this difference between the Syrian and Ukrainian. So they showed the same attitude, whether it's Syrian or Ukrainian. So once they figure out that this is a manipulated image, they immediately change their behavior. So the finding that we have, that there is no significant difference in RT or the donation or the pupil dilation for these different three conditions. And the ANOVA also, it results that the donation was different for the donation when they just realized that the image is not authentic. So in the original image, the average of the donation for all the participants was $7. And then when they found that they were giving an image that is not authentic and not original, it dropped to 3.75 and 5. Okay. So here, the participant lost their empathy once they realized that the image was manipulated by by us in the lab. Okay. And this is really important because with the advance of the AI and how it changed and how it can create content of fake images, now we understand how the user, they have empathy. And now we understand why people, they go into the social media to find news instead of the news in the media, because they are really wanted to see authentic images. And an authentic data set, it's what makes people have empathy. And another thing that we found is, it is not the media that decide for the people. It's the image itself of the refugee that it decide the emotion of how the people react to those. So when we are doing it in a controlled lab, we were able to see this difference. And we were able to see that the ethnicity or the background of the user doesn't really affect how we perceive peoples. And the data set, the original data set, it's what it creates the empathy. So one of the limitations of this study that we have a small sample size, and you know why we were not able to come with a big data set. It's because of all the limitation with all these, different kind of data. But it would be really benefit if we can find 2 different type of refugees with equal story, but same different ethnicity, and then we replicate the same study and see if we can get the same thing. Also, one of the restriction is our participants were from 17 years old to 30. So this is a very young age. And we are wondering what kind of, response we will get if we try different age group. We're also thinking if we replicate this study, or if anyone wants to replicate the study on an Amazon Mechanical Turk. Now, with the Amazon Mechanical Turk, you can test it on a wide range of people, and you can set maybe many countries that you want. The only thing that you can't measure is the eye movement, because with the Amazon Mechanical Turk, the worker will be doing it from their home. So you don't have this option of having it in a controlled lab, measuring their eye movements. So here with the conclusion and what we want to, understand, that the goal was to investigate whether face swapping, before or during, the trial in any, would impact the participant decision and would create an implicit bias, and whether that there is an option of studying refugee informatics in a context of human-computer interaction where you can create displays and also apply computer vision techniques in order to understand how we can help more refugees. Now imagine those studies if it's used more to create more research to advance refugee informatics and understand more. It will make a huge advance in human-computer interaction, and also computer vision research. And it will maybe help with designing application that maybe help refugees, resettlement, integration, maybe to give it to those who have support services, or even to those who have who do the policy making. So this is one of the example, and I'm sure that there are, and I hope that there are more studies into refugee informatics field. I wanted to thank my team, my student, Attar, who worked on me during his master's study, and now he's a software engineer in Walmart, and also my collaborator in Kuwait University, Rimal Bagli. And I also would like to thank you all for coming this Monday day with the first day of the week. And I'm happy to take any question from you. and from those who are in the on the Zoom.
Yeah, we are actually live on YouTube also. But there are no questions from YouTube. Unfortunately, we started a bit too late because of the Wi-Fi issue.
Oh, okay.
So I think that's the reason why we lost some posts on YouTube. Let us check again. Yeah, there are no questions on Zoom.
But this is really like very good so like the other thing in the base times when we see a lot of fake images and we don't know what it is for that. I was curious, like before you allow to measure the future direction, what are the other things you consider? I mean, with the high track, how do you do any other investigation for
Yeah, so there is extensive research on the pupil size and how the pupil size can reflect the cognitive load of the user and how they perform on the task. Especially if you do it in a controlled lab where you really care about the distance of the computer, the light in the room. Then at this point, you don't leave a room for the pupils to change its size unless it reflects how the people think. So there was a study, and there's a very old study, but it really can simplify how the pupil size works. So they give us a person a sequence of digits to memorize. So with every digit that the user was memorizing, they were able to see that the pupil size was increasing because they are kind of, loading these numbers and trying to repeat it in their mind. And then they asked them to rehearse those digits. With every digit they were saying, the pupil size was getting smaller and smaller and smaller because they are kind of like emptying their memory. And this is how the start of people thinking that, okay, pupil dilation reflects cognitive load. Yeah.
Is there a research paper which confirms this?
Yes, there are many research papers on cognitive load and how the pupil size can reflect it. So for example, when you are doing a search task, and let's say that, where is Waldo? An image with one person, and they ask the people to look for where is Waldo. And when you are doing the search, what do you do usually? You do memory. So if I ask you to find your keys and you look in this table, you're not going to go again to this table and look because in your memory, I looked here. So you look into another table. So the same thing is when we are searching on the screen. They found that people, when they do the search, they are also building their memory. So you can see that their pupil size changes. And then when they found the Waldo in the image, you see a spike on their pupil size. It's like, okay, here's the target. So also there is a study, where they recommend you not to take the pupil dilation around the target because that's, the excitement of you finding, what you're looking for. And the previous one is what it measures the memory and the search process.
Is even I'm surprised that separate potential theory is not being applied in. Like you can apply it for evaluating the student's cognition at the time of attending Zoom classes.
Yeah.
Right? There are many other applications. But the surprise is
Yeah, the reason for that is the eye tracking is pricey. So if you wanna test it on the class, you need to have multiple ones, and each one can range that it can be like at least 20,000. So if you wanna buy 2 or 3, it needs a budget, and it needs also a very controlled room. Not very, but like a room with this light, it might affect a little bit. Maybe if we just close maybe third of the amount of the light, it will work. But mainly it's because of the price of the eye tracking.
and probably the permissions IRB approval.
And the IRB, yes, yeah, the IRB.
So you mentioned that you have 14 users for this project.
Mhm.
I was wondering, like how you got your clusters, because you mentioned that they're all very young. I was wondering if they all came from similar races or backgrounds, because that might also affect the instance?
Yes, that's good. Yeah, that's a very good question, actually. And most of our participants were from the campus at SJSU. But when we put the flyer, we made sure that we don't have any participant who is from a Middle Eastern background, because we don't want them to, oh, that's a Syrian person, I'm going to give them more donation than the Ukrainian. We also make sure that we don't have any person with a Ukrainian background. So we were very particular about, who are our participants. We allowed other people who are not from those two countries. We also didn't want any participants who had a refugees background, because we don't want them to also be affected on the studies. Like, oh, I'm gonna give everyone $10. I'm a refugee. I know how this is. So those are the restriction that we put. But I agree with you. Even if we put all the restriction, we are still biased because we are doing it in California. And maybe if we are replicate this study in another state, we will get a different, responses. So we don't know. And this is one of the limitations. So I do agree with you on that. Yeah. Yes. Yes. Exactly. Like, we can't go around and ask people like an interview and just put an eye tracker on them. That if, for example, we do it during this time, okay, now the sun is not very harsh, but if we do it maybe 3 hours ago with another participants, they will get different data from yours just because we're doing it on a different time of the day. Also the noise. So if we do it and there are so many cars passing and this create a noise, it will change how the pupil size. Because even, a knock on the door during the experiment can change people's, oh, someone is. So that's why we also ask them to put their phone on silent, put it away, because, like with this, also especially that they are young, if their phone keeps, ringing, I'm sure that their attention is going to be on that direction. So yeah, eye tracking experiment is really critical and has to be in a control lab, but the result is very accurate because the data is very clear. Any other question?
So I agree, the very relevant study for today. How long did the whole project take from the beginning to the end? Which part was the hardest?
It took us like more than a year. So there are two things that was collecting the data and finding all these refugees, and then create those, finding which one we can do it, and then apply those computer vision technique to create the experiment. Those were the hard. The other thing that was also hard, that our collaborator, Reeb, she was in Kuwait University, so that's 12-hour time zone. So meeting was very difficult, that one of us has to stay up late or the other one has to wake up early morning, like 3 a.m. to meet. So, but she was working here for like 6 months on her sabbatical. That's how, we started this. But then when she moved, it created that, a little bit of slowdown on the experiment. Yeah.
So did you determine statistically significant samples and
So it depends, and that's a good question. So in psychology, a 14 participant is very small number, but in computer science, usually any number above 10 is reasonable. So here we went with 14, so we are, in a safe zone. If you are studying maybe this experiment, you want to replicate it on people who have autism, then you need a huge number. Or dyslexia, you need like 100 people, 150, because to measure the dyslexia, it's not accurate, it's a scale. And you have to get a big group of people to know that, okay, those are dyslexic people. Because if you take 10, maybe they don't have that much dyslexia, so you're not measuring anything. So it depends also on the participant. Those participants were normal adult, and they have normal vision. So that's also a factor. If they come with the complication in their vision, it'll be a problem. So with the eye tracking, you tend not to get participants who are maybe above 40. Even 40 is a young age, but sometimes there are complications in people's vision at this age. So you want to limit the chance that, we're not measuring something else. Okay. Any other question? Thank you.
Okay, so that was a really exciting talk, like, on a very interesting topic. So the next talk is also very interesting. It's about discovering the nuances of music with machine learning. So the talk presents insights into understanding music using machine learning to analyze and categorize various aspects of music. The talk will explore how music is digitally represented using features analogous to building a fingerprint for each song. The presentation then explores various dimensionality reduction techniques for music feature analysis. The speakers present a novel approach using representation learning in lower dimensions to evaluate the efficacy of MEL spectrogram features in capturing music characteristics across diverse languages. By visualizing the features in transformed spaces, the speakers explain how insights can be gained into fine-grained attributes like vocalist timbre, gender, language, and industry prominence, spectral and non-spectral algorithms, including PCA, TSNE, and UMAP, are employed to analyze music datasets. The speaker's findings demonstrate UMAP's superior performance in discerning subtle musical nuances. The research paper that the speakers co-authored on a similar topic won the Best Paper Award at the 10th ICMC, a Springer Conference in 2024, earlier part of the year in January. The audience will discover how machines are learning the language of music, opening doors for new music exploration and analysis tools. So we have two speakers giving the talk on the topic. The first speaker is Samhita Konduri. She is a junior in Palo Alto High School. She is passionate about math and deep learning. And actually, I got the order of the speakers flipped. But anyway, she is passionate about math and deep learning and their applications in media. Apart from research, Samhita enjoys Indian classical singing, debate, and keeping up with current events. The talk will be started by Kriti Pendyala. She is a freshman at University Preparatory Academy in San Jose, California. She won third place in the American Mathematics competition, AMC 10, in her school. She's a ninth grader, but she won the third place in AMC 10 in her school and is a consistent honor roll student. Aside from school, Kriti enjoys writing, Indian classical dance, and vocal music, and is currently preparing for the exams to establish her credentials in these arts. She hopes to grow up to be a software engineer or a professor like her parents. So let's invite Kriti to the podium to give an introduction to discovering the nuances of music with machine learning. Kriti Pendyala.
Good evening. Thank you so much for coming. So, Pendyala already gave a brief intro, but today what we're going to be presenting is discovering the nuances of machine learning. And yeah, let's get started. So you might wonder what machines truly can do with music, because it's somewhat a new topic. And can they group songs by region or artist or gender or the veteran status of the vocalist or the language? And we can do all these things as humans, but can machines learn to do the same? And the answer is yes, they can. And you might wonder how. Well, some algorithms, including TSNE, UMAP, and PCA, can help analyze and create plots using audio snippets. And we'll dive deeper into these algorithms later on into the presentation. So you might be wondering, what is Indian music, especially if you don't have a proper background. And so Indian music varies a lot throughout the different regions of India. And typically in the north, Hindustani music is practiced, while in the south, Carnatic music is practiced. And one of the more formal types of music is Carnatic music, which is mainly practiced in South India. And both Sampita and I are well-versed in Carnatic music, and we're both learning at this time. And there are many different characteristics in Carnatic music, which makes it very interesting and a really good topic to do machine learning on. And they can affect the different types of music being made. For example, timing, pitch, melody, tune, and intonation. Of course, you can also find these in Western music as well. So there's a lot of different aspects in Carnatic music, like I mentioned before. But in this data set, we're specifically working with region, language, artist, and gender. So in our data set, we found a data set that had music from a lot of different types of regions, but mainly we chose 4 main regions. These are from different parts of India, so we have like a pretty good variety. And these also followed the guidelines of our data set. So for example, we wanted data sets with very equal distributions into the different aspects, and these fit our data set the best. And we also have artists who are both veteran or somewhat older artists, and we also have contemporary artists. The vocalist gender was also split half-half. We have male artists and both female artists. And we had 16 artists in total, 4 artists per language, and we had 4 languages. And that is our data set, and that typically sums it up. So you might be wondering, what makes our project stand out from every other project? Well, for one thing, even though we used somewhat common algorithms like PCA, TSNE, and UMAP, they haven't really been used in music, especially not in Indian music, which makes our research really interesting. And because we used a lot of different aspects of Carnatic music or Indian music in general, it also makes our project more valuable. And our analysis is also based off of MEL spectrograms, which is a pretty common way to represent audio. So next, these are our research questions or our goals that we wanted to have in our project. So our first research question was, what can be concluded about the distributions of the MEL spectrogram features extracted from 30-second snippets of music renditions. And our second research question was, how effective are the representation learning and machine learning used for dimensionality reduction at distinguishing the fine-grained attributes of a rendition, such as the artist, their veteran status, language of rendition, and their gender from the mel spectrogram features extracted? So you might be wondering what these goals actually mean. So our aim was to use machine learning to find the correlation and differences between the different types of music in India. And the data set we used had a wide variety of songs with different labels. Our goal was to use different AI algorithms and to see if they could create clusters based on the language, rendition style, etc. And our results could help depict how well machine learning was able to find the nuances of music and audio. So about MFCCs and BFCCs, this is just a brief introduction to them. Obviously, there's a lot more. So for some of our algorithms that we use, we had to convert the data into MFCCs and BFCCs. MFCCs are mel frequency cepstral coefficients, and they help extract the features of data, especially audio snippets. And BFCCs are bark frequency cepstral coefficients, and they're similar to MFCCs in the way that they also can help analyze audio snippets. So now we're moving on to the actual algorithms, or where the magic actually happens. And so we used three main algorithms in our project, which were PCA, TSNE, and UMAP. So the first one we used was PCA, or Principal Component Analysis, and it uses data to create a plot that can help visualize and form clusters, and it's also really useful in dimension reduction. Our second algorithm that we used is TSNE, which is T-distributed stochastic neighbor embedding, and it allows to see data visualization through the use of a plot. However, unlike PCA, TSNE has 2 or 3 dimensions compared to PCA's, I think only 1, which allows for more accurate results in clustering. And the third algorithm that we used is UMAP, or Uniform Manifold Approximation and Projecting, and it allows, it creates a plot that allows, or that uses dimension reduction to show data. And it's really useful because it keeps the basic structure of a plot, even though the dimensions are reduced. And now we also use a few other algorithms that were not as main as the first 3 that we used, but we still decided to include them. And the first one is KDE plots, and Samhita will go more into detail on this later. And we also used autoencoder, and both of these are different ways to analyze plots and data. And then we also use algorithms such as using both TSNE and UMAP in one time, so that we could get the accurate results from both of them to get even better results than they would have produced separately. And that's all I have. So if Samhita would want to come up and do the rest.
Thank you, Kriti. Yeah, so we'll start with talking about our experiments. Kriti already talked about this a little bit, but basically the new thing that we did with this research project is using these established algorithms like TSNE, UMAP, and PCA for subtle aspects of music that have been less explored. For example, the gender of the artist or vocalist. And talking about pre-processing, the data set that we used already had extracted mel spectrogram vectors. So those were the extracted features that we were working with in our analysis. Because one of the aspects of music that we were analyzing was the gender of the artist or vocalist, whether they were male or female, we eliminated all duets in our data set so that we only had 61 songs remaining. And from like the larger song from each artist, we randomly selected a 30-second snippet to reduce the size of the data that we had to work with. So when we concatenated the MEL spectrogram vectors for each 30-second snippet for each of the songs that we were working with, we had 166,400 dimensions or numbers for each song. And that's an extremely large size of data to visualize and observe patterns from. So this is where dimension reduction comes into play. The idea of representation learning and dimension reduction is to reduce the number of dimensions or numbers we're working with, but try to preserve as much of the structure of the data and preserve as many characteristics of the original data as possible. So the first dimension reduction technique we used was PCA, principal component analysis. And PCA really tries to preserve global distances in the data set. So it reduces the dimensions to some principal components. That's the first part of PCA. And the first few of those principal components or dimensions contain most of the data. And as you look to more and more of these principal components, you're covering more of the variance in the data. So first, we reduced these more than 100,000 dimensions into 2 using principal component analysis, or we took the top 2 principal components that the principal component analysis returned. And we plotted this on a scatter plot that you can see up here. As you can see, the global structure of the full MEL spectrogram vectors has been preserved. There's this outlier in the top right corner, the brown X, that stands for a veteran Nagamese artist who's male, and their song is represented by that plot point over there. And because PCA tries to preserve these global distances between points, that point remains on the side. And throughout using dimension reduction, our goal is really to find clusters within these plots. So we can see when we reduce these large dimensions into 1, 2, or 3, can we find patterns in those 2 and 3 dimensions that can give us more insights about gender or veteran status or language region of these artists. So yeah, so the problem we can see with this this plot, even though we do see a few clusterings, like the green points are near each other, which is Nepali songs. The problem is that there's still these outliers, and we're only preserving global distances, and we're not looking at individual local clusters in the data set. So that's where TSNE comes into play. Again, it stands for T-distributed stochastic neighbor embedding. So what TSNE does is it tries to preserve local clusters and distances in the original data set. And it works especially well for nonlinear data like this music data set. So you can see that there is some improvement, especially that outlier that we saw in the PCA plot, which was put on this on the side because we were preserving global distances, is now mixed into the center of the data set, and it's not an outlier anymore. But again, there is not like a good amount of clustering or clear patterns that we can see. And that's because whereas PCA preserves global distances and doesn't really look at local clusters, TSNE only focuses on local clusters, and it's not very good at preserving these global distances. So that's where we tried a combined strategy. We first took some number of principal components that PCA returned, and then shrunk it to 2 dimensions using TSNE just for purposes of visualization, so we could look at a plot of this. So the first plot we can see on the left is a visualization of the top 10 components, or the top 10 principal components that PCA returns us with. And we can see that there is a little more clustering here, especially when with the big red dots, which are female modern artists in the Marathi language. Their points are generally closer together. meaning that they generally have a lot more similarity in their music and their frequency and their rendition styles. Similar patterns can be seen in the second plot where we're visualizing the top 5 components. But again, we still don't see those like very clear clusters of the attributes we're looking at. So this is where we looked at our third approach, UMAP. UMAP does both in one go. It is good at preserving global distances in data, as well as looking at local clusters and distances inside the data set. And the interesting thing about UMAP is that the UMAP reducer can be unsupervised, as in we don't give the UMAP reducer the labels of gender and region, etc., and we just reduce the dimensions, which is how PCA and TSNE work. But there's also a way to use a UMAP reducer where we give it the labels of, oh, this song is by a female artist, this song is by a male artist, and that way we can get even more insights and we can make the UMAP reducer even more efficient. So there are some, again, improvements when we use UMAP. The red dots, again, are closer together. But again, there's not a lot of clustering. So that's where we turn to supervision. And we can see a lot more clear clusters, clearly separating the different attributes we're looking at. We supervise based on, we produced plots where UMAP was supervised by the 4 different attributes we were looking at. First, region or language. You can see that's distinguished based on color. So we have orange all the way at the bottom, meaning that Nagami's music is generally very different and distinct from other languages. One thing we noticed is that Kannada, the blue dots, are a little more spread out, meaning there's a lot more variance in how renditions are produced in that language. Then in plot B, we can see distinctions based on the artist's gender. This is one of the clearest clustering we got, meaning that in terms of when we look at pitch and mel spectrograms, we can really see a difference and find clear patterns between male artists and female artists, which again makes sense because male artists generally have lower pitches when they're singing. And then plot C, we can see the difference based on whether the artist is a veteran, has been in the industry for 50 or more years, or more contemporary, meaning that they're newer to the industry and maybe have a more modern sounding music. So again, we see that distinction in their mel spectrogram vectors. When it comes to vocalists, this, again, we see some better clustering, but it's not as clear as the ones before, which is likely because for each vocalist, we only had 4 songs to work with, and some of those were removed from the data set because of duets and other things like that. So, as I said, the Kannada language, the blue dots in plot A, that's a little more spread out. So we looked at supervised UMAP and what we can discern from that for each language specifically. So the plots we have up here are specifically for the Kannada language, supervised by gender of the artist or their veteran status. And then at the top, there's also an unsupervised, or the plot produced with an unsupervised UMAP reducer. Again, when we use an unsupervised UMAP reducer, the clustering isn't super clear, but especially on plot B, we see a clear difference between the female artists and the male artists, again, because of their pitch differences. One interesting thing we noted is on plot C here, we tried to separate the plots and find patterns based on their veteran status, whether they're contemporary or more veteran. But the blue dots by this artist named Rajkumar are more spread out. And this means that this artist's music specifically spans more variety, and his music some of it sounds more contemporary on the contemporary side of the plot, and some of it sounds a little more older and more veteran sounding. So that was an interesting conclusion we found from this. So the last thing we did, apart from dimension reduction and the scatter plots, is KDE plots. KDE stands for kernel density estimation, and especially to answer our research question on what we can see about how the data set is spread out and how these frequencies and pitches are focused based on different regional languages. KDE plots are especially important for us. So KDE plots look at how the data is distributed and how these pitch frequencies are focused in the data. So what we did is we used autoencoders, which are another type of dimension reduction that especially work when we need to look at the data comprehensively without losing a lot of information. So we used autoencoders. We reduced these large Mel spectrogram vectors to 2 dimensions and plotted those in a KDE plot for the 4 different languages. And as we can see, there are clear differences in how the data is structured and how frequencies are focused based on which language we're looking at, especially between Kannada and Nagamese, which are from 2 very distinct regions in the Indian subcontinent. Nagamese, they're kind of 2 almost centers of where frequencies are focused, whereas Kannada is one more larger circle. So we can definitely see that there's a lot of differences in pitch based on which sub-regions music we're looking at. Yeah, so to answer the research questions we talked about earlier. Sorry. Yeah, so the axis is just the reduced dimensions of our data. So we had over 100,000 Mel spectrogram vectors, and these are the reduced 2 dimensions that we were looking at. So the x-axis is one of the dimensions and the y-axis is the other dimension, and that's true for all of the plots so far. Yeah, so again, one of the problems with this data set that we were using is that it was relatively small. Again, we only had 4 songs per language, 2 female, 2 male artists. So since again, Kriti and I are both, we both learn Indian classical music, we decided to compile our own data set with more songs to have it available for our own experiments and other experiments. So yeah, so we recorded a bunch of songs and compiled them based on their core pitch into 4 different buckets of what core pitch we were using. And this helped with our experiments looking at KDE plots and autoencoders, as I'll show in the next slide. And it will definitely help to have a more robust data set for more Indian classical music analysis, especially for deep learning. We need a lot of data, but when it comes to Indian classical music, there aren't that many large data sets that are useful for deep learning and machine learning experiments. So this will help in improving the amount of data we have available. So yeah, coming to KDE plots and autoencoders, we wanted to look at how our data set looks compared to the other published data set we used. So on the side, I have a plot of autoencoder of the 2 dimensions that autoencoders reduced our data to. Here, instead of using Mel spectrogram vectors, we extracted MFCCs, which Kriti talked about earlier, from our data. And MFCCs are similar to Mel spectrogram vectors in that they're both based on the Mel scale, which is a scale of frequencies. So this plot on the left is the 2 dimensions that we reduced our MFCCs to using autoencoders. And then the plot on the right is the KDE plots generated from those 2 dimensions. So one interesting thing we saw here is that there's actually 2 very distinct sections of the data. And this ended up being correlated with the songs that Kriti recorded and the songs that I recorded. Since especially the whole data set is just us two as artists, that the difference in our rendition style is what ended up being the most distinct thing that autoencoders were picking up on and reducing the dimensions based on. So the circle on the top right is generally the songs that Kriti recorded and compiled, and then the songs on the bottom left are the ones that I sang for. Yeah, so to answer the two research questions that we talked about earlier, first of all, there are definitely lots of reasonable insights that we can find from Mel spectrogram vectors and MFCCs in terms of the subtle aspects of music, like artist gender, the sub-region of where their music is coming from, whether they're a veteran, a singer, or a more contemporary artist, and even when we look at the vocalist specifically. And then for the second research question, definitely, as we can see from the plots, supervised UMAP produces the best results and the most clustering, especially when compared to PCA, TSNE, and unsupervised UMAP. So that's definitely the best representation learning technique. And in the future, again, in our data set, we only looked at the 4 Kannada, Nagamese, Nepali, and Marathi as the 4 languages we were looking at, but definitely we can extend to look at more languages, more regions in India, and also other fine-grained, subtle attributes of music beyond the 4 we studied in this project here. Yeah, thank you to Kriti for working on this project with me, and Dr. Pendyala for his guidance throughout the project and helping out with organizing this talk for us. Thank you. Oh, are there any questions for us? Yeah. Yes. So yeah, that's why, so the data set that we were using, it contains 10-second snippets. So each song that the artist recorded was broken up into 10-second snippets already in the data set, their pre-processing process. So we randomly chose 3 consecutive 10-second snippets to concatenate together and use in our data set. So because we were randomly choosing those 30-second snippets, we try to mitigate for differences between whether you use, say, Anupalavi or Charnam. And especially since the attributes we're looking at here, such as artist gender and whether they're a veteran or contemporary singer, these are things that would stay, or the Pallavi of a contemporary singer and a veteran singer would be distinct just as the Charanam would too.
What was the hardest part of this research and what was the funnest part of research for both of you?
I think the funnest part was probably when we got these clear clusters with supervised UMAP. It was super exciting because especially when compared to the other plots we saw so far, the clusters were significantly better once we used supervised UMAP reducers. And the toughest part, I don't, Kriti can answer this question after, but the toughest part for me was recording the songs because there were like, the entire data set we have published right now is over 1,000 snippets. And it was just Kriti and I's voice for the whole thing. So we had to record a lot of songs in different pitches. Do you want to
You can speak, speak up.
You can come here.
Are there any questions on Zoom? I don't know if yeah, you can talk.
In my opinion, I think the toughest part of the project was probably with the data set because like Samhita said, it's just the two of us and it was really hard to try to adjust our voices to fit into many different Shrutis instead of just the ones that we're comfortable in. And I think the most fun part was actually testing our data set with the different algorithms because obviously it was fun to see how our own voices worked with the algorithms.
Other questions? So we have no questions on Zoom or YouTube. So let us give a round of applause for that. So I request Mr. Konduri, Gangadhar Konduri, to please come and hand over the plaque to Dr. Attar. Dr. Attar gave a great talk today, so if you can. I request that request Dr. Attar to felicitate the two kids. Amita. So, lot of pizza, please feel free to pizza. And so officially the session closes now. Thank you all for coming. And the next event is in Stanford. It's New Frontiers in Computing. The theme is ethical AI, responsible AI, generative AI. So hope to see at least some of you over there. Thanks everyone who are online. I'll close the meeting now. Thank you. Yeah.